close your eyes for a moment and imagine you could shrink yourself down, smaller than the tiniest grain of sand, smaller than a cell, smaller than an atom, plunging into realms where reality itself begins to foam and bubble like a cosmic soup at the very edge of existence. Now reverse that journey. Expand outward, beyond your body, beyond Earth, past our sun, through our galaxy containing hundreds of billions of stars, out into the cosmic web where galaxies cluster together in structures so vast that light itself takes hundreds of millions of years to traverse them. You, right now, exist somewhere in the middle of this incomprehensible scale. But here's what should send a chill down your spine. The difference in size between you and the entire observable universe is roughly the same as the difference between you and the smallest measurable distance in physics. You are suspended in the middle of an abyss of scale so profound that it challenges everything your mind tells you about reality. The universe doesn't just contain you. You are made of the universe at its smallest scales, and you exist within the universe at its largest scales, and both extremes are so bizarre, so utterly alien to your everyday experience, that scientists themselves struggle to comprehend what their own equations are telling them. What if I told you that at this very moment, space itself might be boiling at scales so small that no microscope will ever see it? What if the solid floor beneath your feet is actually more empty space than matter, and that emptiness is anything but empty? What if the galaxies you see in the night sky are just tiny droplets in an ocean of cosmic structure that extends far beyond what we can observe, perhaps infinitely? This is not science fiction. This is the universe we inhabit, described by the best science we have, and the journey through its scales is perhaps the most mind-bending adventure human beings have ever undertaken. Think about this for a moment. Can you truly comprehend something a billion times larger than yourself? Can you visualize something a billion times smaller than an atom? Your brain, magnificent as it is, evolved to understand the scale of predators and prey, of trees and rivers, of distances you could walk in a day. It was never meant to comprehend the scales we're about to explore. Yet here we are, armed with mathematics and physics, peering into both the infinitesimal and the infinite, trying to make sense of our place in this tower of scale that seems to have no end in either direction. The story of how we discovered these scales is itself a journey through human curiosity and ingenuity. For most of human history, we knew nothing of atoms or galaxies. The scale of our understanding extended from the smallest grains of sand to the distant stars, which many believed were merely holes in a celestial sphere just beyond the moon. We thought we were the center of everything, that the universe was made for us and scaled to our understanding. We were catastrophically wrong, and the journey to discovering just how wrong is filled with moments of profound revelation, bitter controversy, and insights so stunning that they forever changed what it means to be human. Let's begin our journey at the bottom of reality, at the smallest scale physics can currently describe. Imagine you have a ruler, but this is no ordinary ruler. You want to measure smaller and smaller things, so you keep dividing your measurements. A meter becomes a millimeter, then a micrometer, then a nanometer as you enter the realm of molecules and atoms. Keep going. A picometer, where you can see the space between atoms. A femtometer, where you're measuring the size of atomic nuclei. Keep going through attometers, zeptometers, yoctometers, diving down into realms where no human instrument has ever directly observed anything. Eventually, you reach something called the Planck length, approximately 1.6 times 10 to the negative 35 meters. This number is so small that it defies analogy. If an atom were expanded to the size of the observable universe, the Planck length would still be smaller than a single atom in that comparison. This is where our current physics breaks down, where the equations we use to describe reality start spitting out infinities and nonsense. At this scale, space and time themselves are thought to lose their meaning. Imagine the smooth fabric of spacetime that Einstein described, the cosmic stage upon which all events play out. Now zoom into the Planck scale, and that smooth fabric becomes what physicists call quantum foam. Space itself is boiling, bubbling with tiny wormholes and fluctuations, appearing and disappearing in timescales so brief that calling them moments seems generous. This is the Planck time, about 5.4 times 10 to the negative 44 seconds. In this foam, The distinction between here and there, between now and then, becomes fuzzy. Virtual particles pop into existence and vanish before they can be observed, borrowing energy from the vacuum itself in a cosmic shell game permitted by Heisenberg's uncertainty principle. This isn't empty space. This is space itself having an existential crisis, unable to decide what it wants to be at any given moment. Do you find this unsettling? You should. The ground of reality, the very foundation upon which everything else is built, is not solid. It's a seething quantum chaos. Some theoretical physicists speculate, and I emphasize this as speculation, that at this scale, the 3 dimensions of space we experience might be joined by additional dimensions, curled up so tightly that they're impossible to detect. String theory, one attempt to unify quantum mechanics with gravity, suggests there could be as many as 11 dimensions of spacetime, with the extra 7 compactified at around the Planck scale. Other theories propose that what we call quantum foam might actually be a sign that spacetime itself is not fundamental, but rather emerges from something even more basic, perhaps a network of quantum information or discrete chunks of spacetime rather than a smooth continuum. Why does any of this matter? Because this is the basement of reality. Everything you see, everything you are, is built on this foundation. The uncertainty and weirdness at this scale ripple upward through every other scale of existence. The fact that virtual particles can briefly borrow energy from nothingness isn't just a curiosity. It's a fundamental feature of how the universe works, affecting everything from the behavior of atoms to the structure of the cosmos itself. Some cosmologists even theorize that the entire universe might have originated as a quantum fluctuation, an incomprehensibly tiny bubble of spacetime that inflated to cosmic proportions in a fraction of a second. If that doesn't make you pause and stare into the middle distance, wondering about the nature of existence, I don't know what will. As we begin to move up in scale, we encounter the first stable structures built from this quantum chaos. Around 10 to the negative 15 meters, roughly a femtometer, we find quarks. These are the fundamental building blocks of protons and neutrons, and they have a peculiar property. You can never observe a quark in isolation. Try to pull quarks apart, and the energy you invest in separating them creates new quarks that pair up with the ones you're trying to isolate. This phenomenon, called quark confinement, means that quarks are forever trapped in their partnerships, bound by the strong nuclear force, one of the 4 fundamental forces of nature. This force is mediated by particles called gluons, and the mathematics describing their behavior is so complex that we can only solve the equations using massive supercomputers. Think about this. You are made of atoms, and atoms are made of protons and neutrons and electrons, and protons and neutrons are made of quarks held together by gluons. And when physicists try to calculate precisely how this works, they need some of the most powerful computers ever built. The very matter of your body emerges from interactions so mathematically intricate that understanding them represents one of the supreme achievements of human intellect. There's something profoundly humbling about that, isn't there? You look at your hand, and it seems so simple, so solid, but it's really a symphony of quantum fields playing out trillions upon trillions of interactions every second, governed by mathematical laws we've only recently begun to understand. Moving up another factor of about 10,000, we reach the scale of atoms, roughly 10 to the negative 10 meters, or 1 angstrom. This is where chemistry happens, where the behavior of electrons in their quantum orbitals determines how atoms bond together to form molecules. An atom is almost entirely empty space. If you expanded a hydrogen atom to the size of a football stadium, the nucleus, a single proton, would be roughly the size of a marble at the center, and the electron would be an even smaller speck somewhere in the outer seats. The rest is emptiness, or rather, it's space permeated by quantum fields and probability distributions. But here's something that should capture your imagination. That electron doesn't orbit the nucleus like a planet around a star. It exists in what's called a quantum superposition, simultaneously inhabiting all possible positions in its orbital until something interacts with it and forces it to choose a location. Before measurement, the electron is best described as a cloud of probability, more likely to be found in some places than others, but not actually located anywhere specific. This isn't because we don't know where it is. It genuinely doesn't have a definite position until something observes it. This is the famous weirdness of quantum mechanics, and it operates at this scale constantly, determining which atoms stick together and which don't, which molecules are possible and which aren't. The world at atomic scales is governed by quantum mechanics, a theory so successful that virtually all modern technology depends on it, yet so strange that even its pioneers were disturbed by its implications. Niels Bohr, one of the founders of quantum theory, allegedly said that if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Einstein, despite his own contributions to quantum theory, never fully accepted its philosophical implications, particularly the idea that reality doesn't have definite properties until measured. His famous protest was that God does not play dice with the universe, to which Bohr reportedly replied that Einstein should stop telling God what to do. This tension at the heart of physics persists to this day. We have two extraordinarily successful theories: quantum mechanics, which describes the very small, and general relativity, which describes the very large. Both have been tested to astonishing precision. Both make predictions that match experimental observations to many decimal places. And yet, they are fundamentally incompatible. When you try to apply quantum mechanics to gravity, or general relativity to quantum fields, the mathematics breaks down. Reconciling these theories is perhaps the greatest challenge in physics, and it matters because at certain extreme scales, like the Planck scale or the center of black holes, both theories should apply simultaneously, and we need to understand what happens there. As we continue upward in scale, we encounter molecules, the chemical compounds made of multiple atoms bonded together. A typical molecule of water, H2O, is about a nanometer across. This is 10 to the negative 9 meters, still far too small to see with visible light, which has wavelengths hundreds of times larger. But molecules are where the complexity of chemistry really explodes. The number of possible molecules is staggering. Carbon, with its ability to form 4 bonds in various configurations, can create molecules of almost unlimited complexity, from simple methane with 1 carbon and 4 hydrogen atoms to proteins containing thousands of atoms arranged in precise 3-dimensional structures, to DNA molecules that can be meters long when uncoiled, containing billions of atoms encoding the information needed to build and operate a living organism. Consider DNA for a moment. Each human cell contains about 2 meters of DNA, coiled and folded and packed with remarkable efficiency into a nucleus just a few micrometers across. That's 10 to the negative 6 meters, the scale where you need a microscope to see anything. If you unwound all the DNA in all the cells in your body and laid it end to end, it would stretch from Earth to the Sun and back more than 300 times. Inside you, right now, there are billions of kilometers of DNA, all compactly stored, constantly being read, transcribed, and translated into the proteins that make you function. The information density is extraordinary. All the information needed to build a human being, roughly 3 billion base pairs, is stored in a molecular structure mere nanometers wide. This brings us to an important threshold in our journey through scales. Somewhere between simple molecules and cells, between the deterministic laws of chemistry and the unpredictable emergence of life, something remarkable happened. Non-living matter organized itself into systems capable of reproduction, metabolism, and evolution. We don't fully understand how this happened. The origin of life is one of the great unsolved mysteries in science. We know it happened at least 3.5 billion years ago on Earth, and possibly earlier. We know the basic requirements: liquid water, organic molecules, energy sources, and time. We've even created some of the building blocks of life in laboratory conditions mimicking early Earth. But the step from complex chemistry to the simplest self-replicating system remains murky. Ask yourself this: at what point does chemistry become biology? Is there a clear line, or is it a gradient? A virus, for instance, sits on the boundary. It has genetic material and can reproduce, but only by hijacking the machinery of living cells. Is it alive? Different biologists give different answers. This ambiguity suggests something profound. Life might not be a binary state, but rather an emergent property that arises gradually as chemical systems become sufficiently complex and integrated. If so, then the universe might be filled with systems at various points along the spectrum from pure chemistry to unambiguous life, and most of it wouldn't look anything like what we're familiar with. The scale of a typical cell is about 10 micrometers, or 10 to the negative 5 meters. This is the scale of single-celled organisms like bacteria and amoebae, and also the scale of individual cells in your body. You are not a single entity but a colony of approximately 37 trillion cells, each one a chemical factory of mind-boggling complexity, containing thousands of different types of molecules engaged in thousands of different reactions, all coordinated with precision that makes our best manufacturing plants look crude by comparison. Each cell reads instructions from DNA, manufactures proteins, generates energy, repairs damage, communicates with other cells, and contributes to the overall function of your body, all while maintaining its own internal organization against the constant tendency toward disorder mandated by the second law of thermodynamics. That last point deserves emphasis. Entropy, the tendency toward disorder, is always increasing in the universe as a whole. Yet living things create and maintain order, building complex structures and patterns. How? By consuming energy and exporting entropy to their surroundings. You eat food, which represents concentrated chemical energy and low entropy, and you excrete waste and radiate heat, which represents dispersed energy and high entropy. The total entropy increases, satisfying the second law, but locally, within your body, order is created and maintained. You are a temporary eddy of organization in the universe's general flow toward disorder, and you maintain yourself only by constantly swimming against the current, powered by breaking down the molecules in your food. Moving up to scales visible to the naked human eye, we enter the world of everyday experience. A millimeter, 10 to the negative 3 meters, is about the size of a grain of sand or a flea. A centimeter, 10 to the negative 2 meters, is about the width of your fingernail. 10 centimeters, a decimeter, is roughly the size of your fist. These are the scales at which your senses evolved to operate, the scales at which you intuitively understand size and distance. Yet even here, there's more than meets the eye. That grain of sand is made of perhaps a billion atoms. The flea, despite being barely visible, contains millions of cells organized into muscles, nerves, a digestive system, and sensory organs capable of detecting the warmth and carbon dioxide of your body from meters away. A meter is about the distance from your nose to your fingertip when you stretch your arm out to the side. It's also, not coincidentally, roughly 1/10,000,000th of the distance from Earth's equator to the North Pole, which is how the meter was originally defined in the 18th century. Humans typically stand between 1 and 2 meters tall, and most things in our built environment are scaled to human proportions. Doorways, chairs, tables, stairs, all are designed for creatures our size. But we share the world with organisms spanning many orders of magnitude in size. The smallest mammals, certain species of shrews and bats, weigh about 2 grams and are a few centimeters long. The largest animal ever known to exist, the blue whale, can exceed 30 meters in length and weigh more than 150,000 kilograms. That's a difference of more than 10 million times in mass, all within the category of mammals, all sharing the same basic body plan of 4 limbs, a vertebral column, and warm blood. Why are animals limited to this particular range of sizes? Physics and biology conspire to set boundaries. As you make an animal smaller, surface area decreases faster than volume. A shrew has such a high surface area to volume ratio that it loses heat extremely rapidly and must eat almost constantly to maintain its body temperature. Much smaller, and it would be physically impossible to consume food fast enough. On the large end, structural strength doesn't scale well. If you doubled the height of every dimension of an animal, its weight would increase 8-fold, but the cross-sectional area of its bones, which determines their strength, would only quadruple. This is why elephants have such thick, pillar-like legs, and why the blue whale, the largest animal, lives in water where buoyancy supports its weight. On land, animals can only get so large before their skeletons can't support them. Dinosaurs pushed this limit but couldn't exceed it by more than a factor of 10 or so beyond modern elephants. Now let's expand our view to larger scales. 10 meters is the height of a 3-story building. 100 meters is the length of a football field or the height of a 30-story skyscraper. At this scale, we're still firmly in the realm of human construction and easy comprehension. But as we approach a kilometer, 1,000 meters, our intuition starts to strain. A kilometer is a distance you can walk in about 10 or 15 minutes, a distance you can see across on a clear day if the terrain is flat. The tallest building ever constructed by humans, the Burj Khalifa in Dubai, is about 830 meters tall. The deepest mine extends about 4 kilometers underground. The depth of the ocean at its deepest point, the Challenger Deep in the Mariana Trench, is about 11 kilometers. These numbers might seem comprehensible, but try to truly visualize them. Imagine standing at the top of the Burj Khalifa and dropping a ball. It would take about 13 seconds to hit the ground, accelerating to over 400 kilometers per hour. Imagine the darkness and pressure at the bottom of the Mariana Trench, where the weight of 11 kilometers of water above you creates pressures more than 1,000 times atmospheric pressure at sea level, enough to crush almost anything we build. Yet life exists even there, specially adapted organisms thriving in conditions that would seem impossibly hostile. The discovery of life in the deep ocean trenches, around volcanic vents, in rocks kilometers underground, in Antarctic ice, and in every extreme environment we've examined has profound implications. It suggests that life is remarkably adaptable and that it might exist in places we once thought sterile. In the subsurface oceans of Europa or Enceladus, in the upper atmosphere of Venus, in the sands of Mars. Earth itself is roughly 12,700 kilometers in diameter, about 13 million meters or 10 to the 7 meters. This is a scale where our intuition completely fails without tools and maps. You cannot see the curvature of Earth from ground level. Even from a commercial airplane at 10 kilometers altitude, the curvature is barely perceptible. It wasn't until humans reached space that we could see our planet as a sphere hanging in the void. That image, Earth rising above the lunar horizon, photographed by the Apollo 8 astronauts in December 1968, is often credited with helping launch the environmental movement. Seeing our world as a finite, fragile sphere rather than an infinite plane of resources changed something in our collective consciousness. Here's something to consider. Earth is the only place in the entire universe where we know with certainty that life exists. This small ball of rock and metal and water, 8,000 miles across, orbiting an ordinary star in the outskirts of an ordinary galaxy, has produced not just life but conscious, intelligent life capable of asking questions about its own existence. How common is this? We don't know. The Fermi paradox asks, if life is common, where is everybody? Our galaxy alone contains hundreds of billions of stars, many with planets. If even a tiny fraction developed life, and a tiny fraction of those developed intelligence, and a tiny fraction of those developed technology, there should be millions of technological civilizations in our galaxy. Yet we see no signs of them. No radio signals, no megastructures, no evidence of stellar engineering. The Great Silence, as it's called, hangs over the cosmos. There are many proposed solutions to the Fermi paradox. Perhaps life is common, but intelligence is rare. Perhaps intelligence is common, but technology is rare. Perhaps technology is common, but civilizations destroy themselves before they can spread to the stars. Perhaps interstellar travel is simply too difficult, the distances too vast, the energy requirements too enormous. Perhaps advanced civilizations exist but are quiet, either uninterested in communication or deliberately hiding. Or perhaps we are, in fact, alone or at least among the first, living in a young universe that has only recently become capable of supporting technological life. Each possibility has profound implications for humanity's future and our place in the cosmos. Let's continue outward. The distance from Earth to the Moon averages about 384,000 kilometers, or roughly 10 to the 8th meters. This is the farthest humans have traveled from Earth. Between December 1968 and December 1972, 24 humans made the journey to lunar orbit or beyond, and 12 walked on the moon's surface. Since then, no human has ventured beyond low Earth orbit. We've been stuck in our planetary neighborhood for over half a century, a sobering thought given the optimism of the Apollo era. The moon is close enough that you can see it clearly with the naked eye, close enough that light takes only about 1.3 seconds to travel from there to here, close enough that we've sent people there. Yet it's also far enough that going there required the largest rocket ever successfully flown and represents one of the supreme achievements of human civilization. The sun sits much farther away, about 150 million kilometers, or 10 to the 11 meters. This distance is called 1 astronomical unit, and it's a convenient yardstick for measuring the solar system. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. This means when you look at the sun, you're seeing it as it was 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd continue orbiting an absent sun, held by gravity that propagates at the speed of light, until 8 minutes later when the gravitational binding would release and Earth would fly off into space on a tangent, doomed to freeze as it drifted away from the warmth that sustains its life. The sun itself is enormous, about 1.4 million kilometers in diameter, which means you could fit about 109 Earths across the sun's width and over 1 million Earths inside its volume. Its mass is about 330,000 times Earth's mass. The sun contains 99.8% of all the mass in the solar system. Everything else, all the planets, moons, asteroids, comets, dust, and gas, accounts for just 0.2%. We orbit around the sun not because we're important, but because it's so massive that its gravity dominates the solar system. At the sun's core, temperatures reach about 15 million degrees Celsius, hot enough that hydrogen nuclei overcome their electromagnetic repulsion and fuse into helium, converting mass into energy according to Einstein's famous equation, E=mc². This fusion reaction has powered the sun for about 4.6 billion years and will continue for about another 5 billion years. Every second, the sun converts about 600 million tons of hydrogen into helium, and in the process, about 4 million tons of matter is converted entirely into energy. This energy radiates outward, taking hundreds of thousands of years to work its way from the core to the surface through a dense plasma, then speeding across the solar system at the speed of light. A tiny fraction of this energy strikes Earth, about 1 part in 2 billion of the sun's total output, and that tiny fraction powers virtually all life on our planet. Plants capture sunlight and convert it into chemical energy through photosynthesis. Animals eat plants or other animals, capturing that stored energy. Weather is driven by solar heating. Ocean currents, wind patterns, the water cycle, all derive from the sun's energy. Even fossil fuels represent captured sunlight, ancient organisms that stored solar energy millions of years ago, now being released in our engines and power plants. Think about this. You are solar-powered. The atoms in your body were mostly forged in stars that exploded before our solar system formed. The energy that powers your cells comes from the sun. You are made of star matter, animated by starlight, standing on a ball of star matter, contemplating the stars. The poet Carl Sagan famously said we are made of star stuff, and he was being quite literal. Every atom of carbon, nitrogen, oxygen, iron, and every other element heavier than helium was created in the nuclear furnaces of stars or in the supernova explosions that marked their deaths. The atoms in your left hand might have come from a different star than the atoms in your right hand. You are an assemblage of ancient stellar debris, recently organized into a pattern capable of wondering about its origins. The outer reaches of our solar system extend much farther than the sun. Neptune, the farthest official planet, orbits at about 30 astronomical units, or 4.5 billion kilometers. At this distance, the sun appears merely as a very bright star, and sunlight takes over 4 hours to arrive. Beyond Neptune lies the Kuiper Belt, a region of icy bodies including Pluto, extending to perhaps 50 astronomical units. Farther still, the Oort cloud, a hypothetical spherical shell of comets surrounding the solar system, may extend as far as 100,000 astronomical units, nearly halfway to the nearest star. This vast space is almost entirely empty, a darkness punctuated by tiny frozen worlds too small and distant to see from Earth without powerful telescopes. The nearest star system to our Sun is Alpha Centauri, about 4.3 light-years away, or roughly 40 trillion kilometers. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers, or 10 to the 16 meters. This is where our intuition doesn't just fail but collapses entirely. There's no way to comprehend such distances through direct experience. Light, the fastest thing in the universe, takes over 4 years to traverse the gap between us and our nearest stellar neighbor. The fastest spacecraft ever built by humans, the Parker Solar Probe, reaches speeds of about 200 kilometers per second at its closest approach to the Sun. At that speed, it would still take about 6,000 years to reach Alpha Centauri. The Voyager 1 probe, launched in 1977 and now in interstellar space, is traveling at about 17 kilometers per second relative to the Sun and will take about 75,000 years to travel the distance to Alpha Centauri, though it's not headed in that direction. These distances pose an enormous challenge for interstellar exploration. Even reaching 1/10 of light speed, which would require technology far beyond our current capabilities, would mean 43 years to the nearest star. At more realistic speeds achievable with current or near-future technology, interstellar journeys would take thousands or tens of thousands of years. This is why proposals for interstellar travel often involve generation ships, where multiple generations would live and die during the journey, or suspended animation, or uploaded consciousness, or tiny probes accelerated by lasers or nuclear pulses. Each approach has enormous technical challenges. Perhaps the Fermi paradox is partially explained by the sheer difficulty of crossing interstellar space. Perhaps civilizations arise, flourish, and die on their home worlds, separated by distances too vast to bridge. Yet despite the distances, stars are not randomly scattered through space. They're organized into galaxies, enormous gravitationally bound systems containing millions, billions, or even trillions of stars. Our galaxy, the Milky Way, is a barred spiral galaxy containing somewhere between 200 and 400 billion stars, though the exact number is uncertain. The Milky Way is shaped like a disk with a bulge in the center, and our Sun sits about 26,000 light-years from the galactic center, roughly halfway out along one of the spiral arms. The disk is about 100,000 light-years across and about 1,000 light-years thick in most places. Try to envision this. Our Sun is one star among hundreds of billions, and it orbits the galactic center at a speed of about 230 kilometers per second, taking roughly 230 million years to complete one orbit. The last time the Sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. One galactic year from now, if the Sun still exists and hasn't changed its orbit, humanity will be gone, likely replaced by something else or simply extinct, and Earth itself might be a very different place. The galaxy rotates, but not like a solid disk. Stars at different distances orbit at different speeds, and the spiral arms themselves are thought to be density waves, regions where stars crowd together temporarily as they orbit, creating the appearance of spiral structure without the stars themselves being permanently in the arms. At the center of our galaxy, and indeed at the center of most large galaxies, lurks a supermassive black hole. The one at the center of the Milky Way is called Sagittarius A star, and it has a mass of about 4 million times our Sun's mass, compressed into a region smaller than the orbit of Mercury. We can't see the black hole directly because nothing, not even light, can escape its gravitational pull once it crosses the event horizon. But we can observe stars orbiting around it, whipping around at tremendous speeds, their orbits revealing the mass of the invisible object they're circling. Some stars orbit so close and so fast that their motion provides one of the best tests of Einstein's general relativity in the strong field regime. Watching these stars over years and decades, astronomers have mapped their orbits with incredible precision, confirming that something very massive and very compact sits at the precise center of our galaxy. In April 2019, the Event Horizon Telescope collaboration released the first image of a black hole shadow, targeting not Sagittarius A star but a much larger black hole at the center of the galaxy M87, about 55 million light-years away. That black hole has a mass of about 6.5 billion solar masses, and the image showed exactly what general relativity predicted: a dark shadow surrounded by a bright ring of emission from superheated matter swirling around the black hole. It was a triumph of both theoretical physics and observational astronomy, confirming predictions made decades earlier and providing direct visual evidence of one of the universe's most extreme objects. Black holes represent a limit of our understanding. At the event horizon, time dilation becomes infinite from the perspective of a distant observer. If you watch someone fall into a black hole, you'd see them slow down as they approach the event horizon, their clock ticking slower and slower, and you'd never actually see them cross it. They'd appear to freeze just above the horizon, their light redshifting to invisibility. From the falling person's perspective, assuming they somehow survive the tidal forces, they'd cross the horizon in finite time and continue falling toward the singularity at the center, a point where density becomes infinite and the laws of physics as we know them break down. We don't know what happens at the singularity because our theories fail there, just as they fail at the Planck scale. General relativity predicts a singularity, but general relativity is a classical theory that doesn't account for quantum mechanics. A complete theory of quantum gravity would presumably resolve the singularity into something less pathological, but we don't yet have such a theory. The Milky Way is not alone in space. It's part of a small cluster of galaxies called the Local Group, which contains about 80 galaxies spread over a region roughly 10 million light-years across. The Local Group is dominated by two large spiral galaxies, the Milky Way and Andromeda, each with its own retinue of smaller satellite galaxies. The Andromeda Galaxy, also called M31, is about 2.5 million light-years away and is the most distant object visible to the naked eye from Earth. When you look at Andromeda, you're seeing light that left there 2.5 million years ago, when our hominin ancestors were just beginning to diverge from other apes. Andromeda is actually approaching us at about 110 kilometers per second, and in about 4.5 billion years, it will collide with the Milky Way. Don't worry, though. When galaxies collide, the stars themselves almost never collide because the distances between stars are so vast. The galaxies will pass through each other, their shapes distorted by gravitational interactions, and eventually they'll merge into a single larger elliptical galaxy that astronomers have playfully dubbed Milkomeda. Beyond the Local Group, galaxies are organized into larger structures. The Local Group is on the outskirts of the Virgo supercluster, a collection of about 100 galaxy groups and clusters containing maybe 47,000 galaxies spread over roughly 110 million light-years. At the center of the Virgo supercluster is the Virgo cluster, a concentration of about 1,500 galaxies located about 54 million light-years from us. The Virgo cluster is so massive that its gravity is actually pulling the entire Local Group toward it, though we'll never reach it because the expansion of space is carrying things even farther away faster than we're falling inward. In fact, the Virgo supercluster itself is just one lobe of an even larger structure called Laniakea, a supercluster of superclusters containing about 100,000 galaxies and spanning 500 million light-years. Laniakea was only defined in 2014, when astronomers mapped the motion of galaxies in our cosmic neighborhood and found they were all flowing toward a region of particularly high mass density called the Great Attractor. The Great Attractor is a gravitational anomaly located roughly 220 million light-years away, in a direction largely obscured by the plane of the Milky Way, which is why it remained mysterious for so long. Observations suggest it's a particularly dense collection of mass, possibly multiple galaxy clusters, but we can't observe it directly because the Milky Way's dust and stars block the view. Laniakea itself is just one structure among many in the observable universe. As telescopes peer deeper into space and further back in time, we see structures on even larger scales. Galaxies are not distributed randomly, but form a cosmic web, a vast network of filaments and sheets surrounding enormous voids. The filaments are made of dark matter, mysterious stuff that doesn't emit, absorb, or reflect light, but whose gravity shapes the distribution of normal matter. Dark matter outweighs normal matter by about 5 to 1 in the universe, meaning that everything we can see, every star, planet, and gas cloud, every human and microbe, represents only about 17% of the matter in the cosmos. The rest is dark, detectable only through its gravitational effects. What is dark matter? We don't know. We've ruled out many possibilities. It's not just normal matter that happens to be dark, like black holes or brown dwarfs, because we can account for the total amount of normal matter through multiple independent methods, and there's not enough. It's not neutrinos, which were once a candidate, because neutrinos are too light and move too fast to have clumped together in the way dark matter has. The leading candidates are exotic particles that barely interact with normal matter except through gravity, perhaps something called WIMPs, weakly interacting massive particles, or axions, or sterile neutrinos. Experiments around the world are searching for these particles, deep underground to shield from cosmic rays, cool to near absolute zero to minimize thermal noise, waiting for the incredibly rare event of a dark matter particle colliding with a detector. So far, nothing definitive has been found, which is either disappointing or constraining our theories, or both. Dark matter is strange, but at least we know it exists. There's something even stranger in the universe. Dark energy. In the late 1990s, two independent teams of astronomers studying distant supernovae made a startling discovery. They were trying to measure the deceleration of the universe's expansion, expecting to find that gravity was gradually slowing the expansion that began with a Big Bang. Instead, they found the opposite. The expansion is accelerating. Something is pushing space apart, overcoming the attractive force of gravity, and that something has been dubbed dark energy. For this discovery, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics in 2011. What is dark energy? Again, we don't know. It might be a property of space itself, a cosmological constant representing the energy of vacuum, Einstein's famous fudge factor that he introduced to make the universe static and later called his biggest blunder, now resurrected as a real phenomenon. It might be a new kind of energy field pervading space, sometimes called quintessence. It might be a sign that our understanding of gravity is wrong on the largest scales, though this seems less likely given how well general relativity has been tested. Whatever it is, dark energy constitutes about 68% of the total energy content of the universe. Let that sink in. Only about 5% of the universe is made of normal matter, the stuff of stars and planets and us. About 27% is dark matter, and about 68% is dark energy. We understand only the smallest sliver of what the universe actually is. The observable universe, the region from which light has had time to reach us since the Big Bang, is about 93 billion light-years in diameter, or roughly 10 to the 27 meters. This is larger than you might expect. The universe is about 13.8 billion years old, so you might think we could see objects at most 13.8 billion light-years away. But space itself has been expanding during the time light has been traveling. So objects that emitted light 13.8 billion years ago are now much farther away than 13.8 billion light-years. The most distant objects we can observe emitted their light shortly after the Big Bang, when the universe was only a few hundred million years old, and those objects are now about 46 billion light-years away, receding from us faster than light because the space between us is expanding faster than light can traverse it. Wait, faster than light. Doesn't that violate relativity? No, because nothing is moving through space faster than light. Space itself is expanding, carrying objects with it, and there's no speed limit on the expansion of space itself. This means there are regions of the universe we will never be able to see, no matter how long we wait, because they're receding so fast that light from them will never reach us. There could be infinitely more universe beyond our observable horizon, regions that are forever hidden from view, entire galactic superclusters, or even regions with different physical laws if certain theories about eternal inflation are correct. We are confined to observe only a finite patch of cosmos, bounded not by an edge but by the speed of light and the age and expansion rate of the universe. The story of the universe begins 13.8 billion years ago with a Big Bang, though that name is somewhat misleading. It wasn't an explosion in space, but rather an expansion of space itself from an extremely hot, dense state. In the first moments, the universe underwent a period of exponential expansion called inflation, growing from subatomic to cosmic scales in a fraction of a second. This inflation smoothed out irregularities and set the initial conditions for everything that followed. After inflation ended, the universe was filled with an extremely hot, dense plasma of fundamental particles. As it expanded and cooled, particles combined to form protons and neutrons, and then nuclei of light elements: hydrogen, helium, and traces of lithium. This primordial nucleosynthesis occurred in the first few minutes after the Big Bang and determined the initial chemical composition of the universe. For the first 380,000 years, the universe was opaque, a roiling sea of plasma where photons couldn't travel far before being absorbed and re-emitted. Then, as the temperature dropped below about 3000 Kelvin, electrons and nuclei combined to form neutral atoms in an event called recombination. Suddenly, photons could travel freely. The universe became transparent, and those photons have been traveling through space ever since, cooling and redshifting as space expands. Today, we detect them as the cosmic microwave background radiation, a faint glow coming from all directions in the sky with a temperature of about 2.7 Kelvin, just above absolute zero. This is the oldest light in the universe, a snapshot of what the cosmos looked like 380,000 years after the Big Bang, and it's one of the most important observations in cosmology. The cosmic microwave background is remarkably uniform, the same temperature in all directions to about 1 part in 100,000. But it's not perfectly uniform. Tiny fluctuations, regions slightly hotter or colder than average, were imprinted by quantum fluctuations in the very early universe, amplified by inflation to cosmic scales. These fluctuations were the seeds of all structure. Regions that were slightly denser than average had slightly stronger gravity, attracting more matter, becoming denser still, in a runaway process that eventually formed stars, galaxies, and galaxy clusters. By mapping the pattern of fluctuations in the cosmic microwave background with satellites like COBE, WMAP, and Planck, cosmologists have measured the universe's age, composition, and geometry with extraordinary precision. The universe is flat, meaning parallel lines remain parallel forever, and it will expand forever, with the expansion accelerating. After recombination, the universe entered a period called the Cosmic Dark Ages, a time when no stars yet existed and the only light was the fading glow of the cosmic microwave background. Gravity was at work, pulling matter together, and the first structures began to form. Dark matter clumped together first, because it doesn't interact electromagnetically and can collapse without radiation pressure holding it apart. Normal matter fell into the gravity wells created by dark matter, forming clouds of hydrogen and helium. About 100 to 200 million years after the Big Bang, the first clouds became dense enough to ignite nuclear fusion. The first stars were born, ending the Dark Ages and beginning the era of reionization. These first stars were probably very different from the Sun. They formed from gas that was purely hydrogen and helium, with no heavier elements because none had been created yet. Without heavier elements, which help gas clouds cool and fragment, the first stars were likely much more massive than typical stars today, perhaps 100 or even several hundred times the Sun's mass. Such massive stars burn brilliantly but briefly, exhausting their fuel in just a few million years before exploding as supernovae. These explosions scattered the first heavy elements, created in the star's cores and in the explosions themselves, into the surrounding space, seeding the next generation of stars with carbon, oxygen, nitrogen, iron, and all the other elements necessary for planets and life. Imagine those first moments of starlight piercing the cosmic darkness, ultraviolet radiation streaming out from brilliant blue giants, ionizing the hydrogen around them, creating bubbles of ionization that grew and merged until, perhaps a billion years after the Big Bang, the entire universe was reionized. Telescopes like the James Webb Space Telescope, launched in late 2021, are designed to observe this era, peering back to the very first stars and galaxies, watching structure formation in action. Early results have already revealed galaxies farther and earlier than expected, suggesting that galaxy formation was a more rapid and efficient process than some models predicted, though our understanding is still developing. Over billions of years, galaxies grew, merging and accumulating mass, their central black holes growing as well, fed by infalling gas and stars. Stars lived and died in generations, each enriching the interstellar medium with heavier elements. About 9 billion years after the Big Bang, in an unremarkable region of a spiral arm of an unremarkable galaxy, a cloud of gas and dust began to collapse. Perhaps it was triggered by the shock wave from a nearby supernova or by the gravitational influence of a passing star. The cloud fragmented, and in one fragment, our sun was born, surrounded by a disk of gas and dust. Within that disk, dust grains collided and stuck together, growing into pebbles, then boulders, then planetesimals. These planetesimals collided and merged in violent impacts, eventually forming the planets. Earth coalesced about 4.5 billion years ago, a ball of molten rock and metal, bombarded by asteroids and comets. A Mars-sized object called Theia is thought to have collided with the young Earth in a glancing blow, vaporizing itself and a chunk of Earth's mantle, throwing debris into orbit that coalesced into the Moon. Eventually, the bombardment slowed, the surface cooled, water condensed into oceans, and somehow, in those oceans or perhaps in subsurface hydrothermal vents or warm little ponds or some other environment, life began. We don't know exactly when or how, but by 3.5 billion years ago, maybe earlier, life was established, and it has been evolving and diversifying ever since, surviving multiple mass extinctions, adapting to changing climates and continents, eventually producing organisms capable of looking up at the stars and asking where they came from. Here we are, then, the universe contemplating itself. In your brain, roughly 86 billion neurons are connected by something like 100 trillion synapses, creating patterns of electrical and chemical activity that somehow give rise to consciousness, to your subjective experience of being you. We don't understand how this works, at least not fully. The hard problem of consciousness, why there is something it's like to be you rather than everything just happening in the dark, remains unsolved. But consciousness arose through evolution in the specific environment of Earth's biosphere, shaped by the need to survive and reproduce, and it has granted us a remarkable ability. We can understand, at least partially, the universe we inhabit. Think about what that means. Matter and energy, organized by the laws of physics over billions of years, have arranged themselves into a pattern, that can comprehend those very laws. The universe has created within itself structures capable of asking why there is something rather than nothing, capable of discovering quantum mechanics and general relativity, capable of building telescopes and particle accelerators to probe the largest and smallest scales of reality. This might be common in the universe, consciousness and intelligence arising wherever conditions permit, or it might be staggeringly rare, perhaps unique to Earth, at least in this galaxy or even the observable universe. We don't know, and that uncertainty is both humbling and profound. As we contemplate the full scale of the universe, from quantum foam to superclusters, certain patterns emerge. The laws of physics appear to be the same everywhere, from the smallest scales to the largest. Symmetries and conservation laws govern the behavior of particles and fields. Gravity shapes the structure of spacetime and the distribution of matter. Quantum mechanics introduces uncertainty and weirdness at small scales, but those quantum effects average out to produce the predictable classical world of our everyday experience. The universe is comprehensible, describable by mathematics, and that fact itself is mysterious. Why should the universe be mathematical? Why should the patterns we discover in one domain apply to others? Why should we, limited biological creatures, be capable of understanding anything at all about reality? The physicist Eugene Wigner wrote about the unreasonable effectiveness of mathematics in the natural sciences, noting that mathematical structures discovered purely abstractly often turn out to describe physical phenomena with uncanny accuracy. General relativity is based on Riemannian geometry, developed decades earlier for purely mathematical reasons. Quantum mechanics uses Hilbert spaces and operator algebras. String theory employs exotic mathematical structures from topology and differential geometry. Why does math work so well? One answer is that we notice the mathematics that works and ignore what doesn't, a kind of selection bias. Another is that the universe is fundamentally mathematical, that physical reality is in some sense a mathematical structure, and our brains, having evolved within that structure, have developed an intuition for the mathematics that describes it. Neither answer is fully satisfying, and the relationship between mathematics and physics remains a deep mystery. As our understanding has grown, so have the questions. The more we learn, the more we realize we don't know. Dark matter and dark energy constitute 95% of the universe, yet we don't know what they are. We don't have a theory of quantum gravity. We don't know if the universe is finite or infinite, whether it's part of a multiverse, whether the laws of physics could have been different or are somehow necessary. We don't know if consciousness is unique to biological brains or could exist in other substrates. We don't know if life exists elsewhere or if we're alone. We don't know if the universe had a beginning in the absolute sense or if the Big Bang was just a transition from some prior state. We don't know what happened before the Big Bang or if that question even makes sense. Consider the anthropic principle, the observation that the universe's properties seem finely tuned to allow the existence of life. The fundamental constants of physics, things like the strength of gravity, the mass of the electron, the charge of the proton, if any of these were even slightly different, stars might not form, or chemistry might not work, or the universe might have collapsed immediately after the Big Bang or expanded so fast that no structures ever formed. Some cosmologists interpret this as evidence for a multiverse. Perhaps there are countless universes with different properties, and we find ourselves in one that permits life because those are the only ones that contain observers. Others suggest it points to design or some deeper principle we haven't discovered. Still others argue it's just a tautology. Of course we find ourselves in a universe compatible with our existence, because otherwise we wouldn't be here to observe it. These are deep waters, philosophical as much as scientific, and they show how the quest to understand the scale of the universe leads inexorably to the most profound questions we can ask. Why does anything exist? What is the nature of reality? What is our place in the cosmos? Science provides answers to specific questions about mechanisms and relationships, about how things work and how they're connected, but it reaches limits when confronting questions of ultimate meaning or purpose. That doesn't mean such questions are invalid. It means they require tools beyond science. Philosophy, introspection, perhaps something we haven't yet imagined. Let's return to where we started, to you, sitting or standing wherever you are, existing at a particular scale in this tower of reality that extends from quantum foam to superclusters. You are made of atoms forged in stars, arranged into molecules, cells, and organs by billions of years of evolution. You exist on a planet orbiting a star in a galaxy filled with hundreds of billions of stars, itself part of a local cluster, a supercluster, a cosmic web extending across billions of light years. Zoom out far enough, and you vanish. Earth vanishes, even our galaxy becomes a speck. Zoom in far enough, and you vanish again, dissolving into atoms, then particles, then quantum fields fluctuating in the void. At both extremes, the solid, tangible reality of your everyday experience disappears. Yet here you are. You exist. You think and feel. You wonder about the universe. And in wondering, you participate in one of the universe's most remarkable achievements: self-awareness. Matter has organized itself into a form that can reflect on its own existence. This happened at least once, here on Earth, and possibly countless times across the cosmos. Every organism that's ever lived, every thought that's ever been thought, every emotion ever felt, all of it emerged from the interplay of particles and forces governed by the laws of physics. Yet somehow none of it reduces to mere physics. The whole is not just greater than the sum of its parts. It's categorically different, exhibiting properties that cannot be predicted from the properties of the components alone. This emergence is everywhere in the universe. Quarks combine to form protons with properties not predictable from quark properties alone. Atoms combine to form molecules with novel properties. Molecules form cells. Cells form organisms. Organisms form ecosystems and societies. At each level, new patterns and behaviors emerge. New laws become relevant. New descriptions become necessary. You can't understand a cell just by knowing about atoms. and you can't understand an ecosystem just by knowing about cells. Each scale has its own appropriate description, its own emergent phenomena, and the universe appears to be fundamentally hierarchical, with each level building on the ones below while exhibiting autonomy from them. Does this hierarchy extend beyond what we know? Below the Planck scale, does something else exist, some deeper level of reality from which space-time emerges? Beyond the observable universe, are there structures on even larger scales, infinite nesting of multiverses or cycles of big bangs and big crunches? Some theories suggest that our universe might be a simulation running on a substrate we can't directly observe, or a hologram projected from information encoded on a distant boundary, or a quantum fluctuation in an eternal multiverse. These ideas are speculative, often untestable with current technology, but they remind us that our understanding is provisional, always subject to revision in light of new evidence or insights. The history of science is a history of discovering that we're not as central or important as we thought. Copernicus showed that Earth orbits the Sun, not the reverse. Galileo's telescopes revealed that the planets are worlds, not mere points of light, and that the Milky Way is composed of countless stars. Hubble demonstrated that the spiral nebulae are distant galaxies, not clouds within our own, expanding the universe from the Milky Way alone to billions of galaxies. Cosmology in the 20th century revealed the Big Bang, cosmic expansion, the cosmic microwave background, dark matter, and dark energy, painting a picture of a universe far stranger and more vast than anyone had imagined. Each discovery displaced us further from the center, and there's no reason to think this process is complete. Perhaps consciousness and intelligence are common in the universe, and we're unremarkable in that respect too. Or perhaps they're so rare that we might be the only instance in the observable universe, in which case we carry a heavy responsibility. If we're the only ones who know the universe exists, who can understand and appreciate it, then our extinction would be a cosmic tragedy, the universe losing its only witness, at least locally. This thought should inspire both humility and determination. Humility because we're so small and fragile, determination because we might matter more than our size suggests. What does the future hold? On human timescales, the universe seems stable and unchanging, but over longer periods, change is inevitable. The Sun will exhaust its hydrogen fuel in about 5 billion years, swell into a red giant, and probably engulf Earth or at least render it uninhabitable. Long before that, increasing solar luminosity will boil away Earth's oceans in perhaps 1 billion years. If humanity or our descendants still exist, we'll need to leave Earth, perhaps settling Mars or moons of the outer solar system, or building habitats in space, or moving to other star systems entirely. The challenges are daunting, but the history of life is a history of colonizing new environments, and there's no fundamental reason we couldn't continue that process into space given sufficient time and resources. On even longer timescales, stars themselves will die. The smallest, faintest red dwarfs can burn for trillions of years, but eventually they too will exhaust their fuel. Star formation will continue as long as there's gas to form stars, but the universe's gas supply is finite, and the expansion driven by dark energy will make it harder for galaxies to acquire new material. Perhaps 10 trillion to 100 trillion years from now, the last stars will form. After they die, the universe will enter a degenerate era dominated by stellar remnants. White dwarfs, neutron stars, black holes. These objects will persist for unimaginable lengths of time, but they too are not eternal. Protons might decay on timescales of 10 to the 36 years or longer, if certain theories are correct. Black holes will evaporate through Hawking radiation, though the process is incredibly slow. A black hole with the Sun's mass would take about 10 to the 67 years to evaporate. The supermassive black holes at the centers of galaxies would take even longer. Eventually, perhaps 10 to the 100 years from now, the universe could reach a state of maximum entropy, a cold, dark, dilute sea of photons and leptons and perhaps decayed proton remnants, spread so thin that interactions are vanishingly rare. This is the heat death of the universe, the final equilibrium state where nothing interesting can happen because there's no energy differential to drive processes. It's a bleak vision, though so far in the future that it's almost meaningless to contemplate. but it follows from our current understanding of thermodynamics and cosmology. Entropy increases, and there's no known mechanism to reverse that on cosmic scales. The universe will not end in fire, but in an endless, freezing whimper. Of course, this assumes our current understanding is correct, and history suggests we should be cautious about such assumptions. We've been wrong before, sometimes spectacularly so, and future discoveries could completely change our picture of the universe's fate. Maybe dark energy will change its behavior, leading to a big rip where expansion accelerates until it tears apart galaxies, stars, planets, atoms, and finally space-time itself. Maybe expansion will reverse, leading to a big crunch where everything falls back together. Maybe the universe undergoes cycles of expansion and contraction, each big crunch followed by a new big bang. Maybe the vacuum we inhabit is metastable, and a quantum fluctuation could trigger a decay to a lower energy state, a bubble of new physics expanding at the speed of light, rewriting the laws of nature and destroying everything in its path. These scenarios are speculative but not impossible, reminders that the universe can surprise us. In the face of such vastness and uncertainty, how should we respond? Some find the scale of the universe terrifying, a source of existential dread. If we're so small and the universe so large and indifferent, what does anything matter? But others find it inspiring, even liberating. Yes, we're tiny, but we're also part of something vast and ancient and beautiful. We're a way for the cosmos to know itself, as Carl Sagan said. Our actions might not matter on cosmic scales, but they matter to us, and that's enough. Meaning is something we create, not something we discover inscribed in the stars. The universe doesn't care about us, but we can care about each other and about the universe itself. Science, at its best, is an expression of that care, a systematic effort to understand the universe on its own terms, to set aside our preconceptions and biases and see what's actually there. It requires humility, the willingness to be wrong, the recognition that nature doesn't care about our preferences or intuitions. It also requires creativity, the ability to imagine new possibilities, to see patterns others have missed, to ask questions nobody thought to ask. And it requires community, because science is a collective enterprise, building on the work of thousands of researchers across generations, each contributing a piece to an ever-expanding mosaic of understanding. The scale of the universe is one of the great discoveries of that enterprise. A few centuries ago, we didn't know about atoms or galaxies or the Big Bang. Now we can describe the universe from the Planck scale to the scale of superclusters, tracing matter and energy through 40 orders of magnitude or more. We've discovered that the laws of physics are universal, that the same processes that govern falling apples also govern orbiting planets and colliding galaxies. We've found that we're made of recycled star stuff, that the atoms in our bodies have been through multiple generations of stars and supernovae. We've learned that the universe had a beginning and has been evolving ever since, that it's much larger and older than Earth, that we inhabit a remote corner of an unremarkable galaxy in a vast cosmos. These discoveries have practical implications. Understanding atomic physics led to transistors and computers. Understanding nuclear physics led to both nuclear power and nuclear weapons. Understanding general relativity is necessary for GPS systems to work accurately. Understanding cosmology helps us grasp our origins and possible futures. But beyond practical applications, these discoveries satisfy a deep human need to understand, to make sense of the world, to find our place in the grand scheme of things. They enrich our lives, expand our perspective, and connect us to the larger universe. Consider the experience of looking up at the night sky, far from city lights, and seeing the Milky Way stretched across the darkness, a river of stars. Ancient peoples saw that band of light and wove stories around it, imagining gods and heroes and cosmic dramas. Now we know what it really is. Our view from inside a spiral galaxy, looking edge-on through the disk, seeing the combined glow of billions of stars too distant to resolve individually. That knowledge doesn't diminish the wonder. If anything, it enhances it. You're not just looking at lights in the sky. You're looking across thousands of light years, seeing stars as they were long ago, some already dead, their light still traveling toward you. You're seeing the structure of the galaxy, the spiral arms where new stars are forming, the dust lanes where clouds of gas obscure the light. You're seeing history and scale and process all at once. And when you look at the darkest patches between the stars, what are you seeing? Mostly emptiness, space itself, but that space is not truly empty. It's permeated by quantum fields, by dark matter, by the cosmic microwave background radiation, by gravitational waves rippling outward from distant cataclysms. It's expanding, carrying galaxies apart, driven by dark energy. The darkness is full of invisible structure and activity, and we've only begun to map it. One of the most profound realizations from studying the scale of the universe is how much we still don't know. We've come so far, yet the frontier of ignorance keeps receding faster than we can advance. Every answer raises new questions. Why these laws of physics and not others? Why these constants? What is dark matter? What is dark energy? What is consciousness? How common is life? Are we alone? What happened before the Big Bang? What lies beyond the observable universe? Is there a theory that unifies all of physics? Can we reconcile quantum mechanics and general relativity? What is the ultimate fate of the universe? These questions drive ongoing research in physics, astronomy, cosmology, and related fields. Experiments in particle accelerators smash protons together at nearly the speed of light, recreating conditions that existed fractions of a second after the Big Bang, searching for new particles and forces. Detectors deep underground watch for dark matter particles. Gravitational wave observatories listen for ripples in spacetime from colliding black holes and neutron stars. Telescopes observe the most distant galaxies, studying their formation and evolution. Satellites map the cosmic microwave background with ever-increasing precision. All of this is an effort to fill in the gaps in our understanding, to probe the edges of the known, to discover what else is out there. But here's something worth pondering. Maybe some questions are unanswerable, not because we lack the technology or intelligence, but because they're fundamentally beyond the reach of science or reason. Maybe the universe is under no obligation to make sense to us. Maybe there are truths we cannot access because we're embedded within the system we're trying to understand, like a character in a novel trying to understand the author. Or maybe not. Maybe given enough time and effort, we can understand anything, at least in principle. We don't know the limits of knowledge, and perhaps the only way to find them is to keep pushing. Throughout this journey from quantum foam to superclusters, one theme recurs. The universe is stranger than we imagined and probably stranger than we can imagine. Quantum superposition, entanglement, wave-particle duality, relativistic time dilation, curved spacetime, black holes, dark matter, dark energy, cosmic inflation. Each of these concepts defies everyday intuition. Yet they're all supported by rigorous mathematics and extensive experimental evidence. The universe doesn't care whether its behavior seems reasonable to creatures who evolved to throw spears and gather berries. It is what it is, and our job is to figure it out as best we can, using whatever tools we can devise. There's a certain audacity in the scientific enterprise, a willingness to question everything, to challenge authority, to follow evidence wherever it leads. This attitude has brought us from ignorance and superstition to a detailed, quantitative understanding of reality at scales ranging from the subatomic to the cosmic. It's not complete. It probably never will be complete. But it's progress, real and undeniable progress, and it stands as one of humanity's greatest achievements. As we conclude this exploration, let's return once more to you, to your place in this hierarchy of scale. You contain multitudes, trillions of atoms, billions of cells, countless thoughts and memories and experiences. You're part of a biosphere, an ecosystem, a planet, a solar system, a galaxy, a supercluster, a cosmic web. Information flows through you, from genes to proteins to cells to organs to systems to behavior. You process energy, temporarily decreasing your local entropy at the cost of increasing it elsewhere. You perceive and think and feel. You wonder about the universe. And the universe, through you, wonders about itself. This is not mysticism or poetry, though it might sound like it. It's a literal truth. You are a configuration of matter and energy, governed by the laws of physics, and you are contemplating those very laws and that very configuration. The universe has organized itself into a form capable of self-reflection. That happened here on this small world orbiting an ordinary star, and maybe it's happened elsewhere too, maybe countless times. Maybe we're surrounded by other consciousnesses also puzzling over their existence, or maybe not. Maybe we're rare or unique, a singular flowering of awareness in an otherwise unconscious cosmos. Either way, we're here, and we're asking questions, and that matters. It matters because understanding is valuable in itself, because knowledge enriches life, because we're driven by curiosity and wonder, because exploring the universe and our place in it is part of what makes us human. The scale of the universe, from the smallest to the largest, from quantum foam to superclusters, is a story of hierarchy and emergence, of laws and randomness, of structure arising from chaos, of complexity building on simplicity, of consciousness emerging from matter. It's a story that's still being written. Every observation, every experiment, every new theory adds to our understanding or corrects our misunderstanding. The picture we have today is clearer and more detailed than at any point in history, but it's still incomplete, still fuzzy at the edges, still punctuated by mysteries and unknowns. That's exciting. It means there's more to discover, more to learn, more wonders waiting to be revealed. So when you look up at the stars, remember that you're looking across distances so vast that light, the fastest thing in the universe, takes years or millennia or millions of years to traverse them. Remember that those stars are suns like ours, perhaps with planets, perhaps with life. Remember that you're seeing the past, that the light entering your eyes left those stars long ago, before you were born, maybe before humans existed. Remember that the atoms in your body were made in stars, that you're star stuff contemplating the stars. Remember that space itself is expanding, carrying galaxies apart, that the universe had a beginning and will have an ending, or perhaps an endless future of cold and darkness. Remember that at the smallest scales, reality becomes probabilistic and strange, that particles can be in multiple places at once, that the vacuum seethes with energy, that the ground of existence is not solid but shifting. Remember that most of the universe is invisible, dark matter and dark energy whose nature we don't understand. Remember that we're a young species on a small planet, that we've only just begun to explore the cosmos, that there's so much we don't know. And remember that despite all our smallness and ignorance, we've managed to figure some of it out. We've measured the universe's age and size. We've mapped its large-scale structure. We've traced its history from the Big Bang to the present. We've discovered the laws governing its behavior. We've built a framework for understanding reality that works, that makes predictions we can test, that gives us power to shape our environment and our future. This is an astonishing achievement for evolved apes on a rocky planet, and it should give us both pride and humility. The journey through the scales of the universe is ultimately a journey of perspective. It shows us where we fit in the grand scheme of things. Not at the center, not at either extreme, but somewhere in the middle, large enough to contain multitudes, small enough to be contained by them. It reveals the universe as a place of almost unimaginable vastness and variety, yet governed by comprehensible laws, accessible to investigation, yielding its secrets to patience and cleverness and hard work. What else is out there, waiting to be discovered? What new scales might we find? What new phenomena? What new laws? What will the universe look like through the eyes of future generations, armed with better instruments and deeper theories? What will they think of our current understanding, our blind spots and misconceptions? Will they look back at us the way we look back at ancient astronomers who thought the stars were holes in a celestial sphere? Probably. And that's fine. That's how progress works. Each generation builds on the last, seeing farther because they stand on the shoulders of giants. The story of the universe, from quantum foam to superclusters, is a story we're telling together, across time and space, each contributing what we can, each pushing the boundary of knowledge a little farther. It's a magnificent story, full of wonder and mystery, and it's far from over. So look around you. Look at the floor beneath your feet, solid yet mostly empty space, atoms held together by electromagnetic forces, nuclei tiny and dense, surrounded by electron clouds, all of it dancing to the quantum tune. Look at your hands, made of cells, made of molecules, made of atoms, made of particles, made of fields, all the way down to the quantum foam at the foundation of reality. Look up at the sky, at the sun, our star, one among hundreds of billions in the galaxy one among hundreds of billions in the observable universe, all of it expanding, evolving, changing on timescales from the infinitesimal to the cosmic. You are here, now, in this moment, embedded in scales beyond comprehension, made of the universe, part of the universe itself in one of its infinite configurations. The quantum foam bubbles beneath you. The superclusters sprawl above you, and you stand in the middle, conscious and curious, asking questions, seeking answers, marveling at the sheer improbability and magnificence of it all. This is the scale of the universe, from the smallest to the largest, from the briefest to the eternal, and you, right now, are participating in it, experiencing it, thinking about it. That's extraordinary. Don't ever lose sight of that wonder. The universe is vast and strange and beautiful, and we're privileged to be here, to witness it, to try to understand it. Keep looking. Keep questioning. Keep wondering. There's always more to discover, always new frontiers, always mysteries waiting at the edges of the known. The journey has only just begun.